Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to look at the energy required to remove an electron from a neutral atom. Now there are definitely trends to be found here, so let's get started. Our official definition for ionization energy is the energy that is required to remove 1 mole of electrons from 1 mole of atoms in the gas phase. Now, more commonly, we think of this as just the energy needed to remove an electron from a neutral atom. One thing to know about ionization energy is that it is always going to be positive because it is going to require at least some energy to overcome the electron's attraction to the positively charged nucleus. Our trend in ionization energy is to decrease as we move down the periodic table. As we move from left to right, ionization energy increases. So ionization energy decreases moving down a group, mostly because that valence electron that you are removing is farther away from the nucleus. However, it is also experiencing extra shielding the more core electrons it has. So a valence electron on rubidium is easier to remove than sodium because that valence electron is farther away from the nucleus and there are more core electrons shielding it from the attraction to the nucleus. Now let's talk about how ionization energy increases as we move from left to right across a period. We already know that the alkali metals are ready to lose an electron because then they gain the stability of the noble gas configuration, the full outer shell. However, remember, as we move across a period, the attraction that the electron feels to the nucleus also increases because we are not increasing the shielding by the core electrons, but we are increasing the positive charge in the nucleus. This makes it a little more difficult to remove that electron. There are some common exceptions to this rule that I want to discuss. The first is if you look at ionization energy of group 16, you will see that ionization energy decreases a little bit. This has to do with the organization of the electrons in the p orbital. So let's take nitrogen and oxygen as an example. For nitrogen, if I'm just looking at the p orbitals, for nitrogen's case that'd be 2p. Nitrogen has 3 electrons in the 2p orbital. Oxygen has 4 electrons in the 2p orbital. Removing one of these p orbitals from nitrogen does not break the trend we see in ionization energy. However, when I remove an electron from the 2p orbital for oxygen, I gain stability. I now have 3 unpaired electrons, which means there is less repulsion experienced by those electrons. This small gain in stability means that ionization energy drops just a bit for oxygen or the group 16 elements. There is one other exception that I want to discuss, and that is how when you move from group 2 to group 13, the ionization energy again drops just a little bit. So let's compare beryllium to boron. In beryllium, you have 2 electrons in the 2s orbital. In boron, you have 2 electrons in the 2s orbital and 1 electron in the 2p orbital. Because this electron in the 2p orbital is a little farther away from the nucleus and is being shielded by these 2s electrons, it's a little bit easier to remove. So we see another small drop in ionization energy as we move from beryllium's group to boron's group. We see again how the shielding by those core electrons can affect the behavior of the valence electrons. Now, chemists usually focus on the valence electrons, but we cannot discount the contribution made by those core electrons. I hope you found this video helpful, and thanks so much for watching.